Chapter 23, Our Milky Way Galaxy. All right, so this is not a picture of the Milky Way. In fact, one of the things that we're going to talk about is the fact that we can't see the Milky Way like this ever because we're part of the Milky Way. All right, so this is just another spiral galaxy similar to the Milky Way, and you know, this would be seen, you know, like if you were looking down the axis of rotation, right here in the middle would be the axis of rotation, and the spiral arms are extending outward. All right, so we'll talk about looking at different galaxies, comparing them to the Milky Way. All right, so these are the different things that we're going to talk about in this chapter. All right, so this starting out, when we look out into the night sky, okay, so this is an artist's rendition of what the galaxy looks like. It's actually not bad, and so this would be our position in the Milky Way. We're about 2/3 from the center out. If you take, you know, the radius from the radius of the galaxy to go from the center of the galaxy to the very, very edge, we're about 2/3 of the way out. All right, and so these red arrows here are showing, you know, the view outside of the plane of the galaxy. So, you know, if you were in the northern hemisphere, there's lots of things to look at in these regions, and in the southern hemisphere, there's lots of things to look at in these regions. But when you look in the regions where the blue arrow is and the white arrow, there you're actually looking into part of our galaxy. Like when you look in the night sky, and you see this hazy region that is in the exact same position night after night after night. That's the Milky Way, right? It's always in the same positions. It covers the exact same constellations, and really what it turns out to be, is looking at our galaxy edge on. In fact, if we look in this direction, the direction of the white arrow, we're actually looking towards the center of our galaxy. And so that's, it turns out, and we'll learn how we determine this. A guy named Shapley was the one who originally discovered this. Anyhow, this is actually in the direction of Sagittarius, the constellation Sagittarius. All right, and then in the opposite direction, that's just looking out into the last 1/3 of our this side of the disk. Okay, so you know, there's the disk is of course three-dimensional. Anyhow, that's what we see, and so this is showing, you know, from our perspective, looking into the galaxy. See, it's thickest in the region. It doesn't look like this when you look into the night sky, by the way. You know, it's spread across the constellations, but in the direction of Sagittarius, it is thickest. I guess would be the best description. All right, so that is you know, that's what we see, and so when we look out at here's another spiral galaxy. This is actually the nearest spiral galaxy to us. This one is called Andromeda. This is actually another galaxy right here. What is that one called? I think that one's called Triangulum. Anyhow, that's not that important. So this is what we think the Milky Way would look like if we were far enough away from it. There are some galaxies, you know, maybe a handful of galaxies that are closer to us, and they're in fact in orbit around the Milky Way. They are little dwarf galaxies. They're generally irregular dwarf galaxies, and so this is really the first large galaxy near the Milky Way. And it turns out it's actually about twice as big as the Milky Way, so there's twice the number of stars in this. Anyhow, we're going to determine how we found the distance to this. In fact, some of the stuff we're going to learn about today, in chapter 23, will actually give us the distance to the nearby galaxies. All right. It has to do with Cepheid variables, as we're going to find out. All right, so here's another spiral. So this is Andromeda. We're looking at it kind of at a little bit of an angle, so you can see the spiral arms. There's the large galactic bulge, as it's called, in the center. All right, and then this is looking more down the axis of rotation, right? You can see the spiral arms are winding around this galaxy, and then there's one, in this second picture. This is a completely different galaxy, of course, and this is looking edge on. So there's the galactic bulge, and there are the spiral arms. By the way, not all galaxies look like this. Okay, they're not all spirals. In fact, I had just mentioned a little while ago that there were these galaxies that are in orbit around the Milky Way, just a handful of them, and they are what we would call dwarf irregular galaxies. They don't have a regular shape. Two of them actually we've talked about already, the large and small clouds of Magellan in the southern hemisphere. I'm pointing to the southern hemisphere as though this is our galaxy. It's not, of course. But remember, what we do is we look at these other spiral galaxies, and then we look to compare what we know of our galaxy and try to get a general picture of our galaxy. All right, so let's move on. So there was the guy who discovered. This was about more than 200 years ago. A guy named Herschel, who discovered the planet Uranus, also did some other work. In fact, he's the first one that we know of to basically just count the stars and make a map of the Milky Way. Now he had no idea what he thought. He was just mapping, the entire universe. And notice he puts the sun relatively close to the center. The other thing that he doesn't realize is, and we certainly know this, and we've only known this for about 100 years or so, that there's a great deal of gas and dust that obscures our view in certain directions. The directions where the Milky Way, where the main disk of the galaxy is from our vantage point. So this was Herschel about 200 years ago or so, maybe a little bit more than that, and 250 years ago. And he came up with this picture. This was an amazing accomplishment for the time. He literally just counted stars and then mapped, put little dots of over 3,000 stars, and he came up with this picture, which is not bad. I mean, it's not exactly the representation that we would in modern times would view of as our galaxy, but it took us a while to get to the point where we understood the shape of the galaxy, and a lot of that has to do with the knowledge that there's a lot of gas and dust that obscures light in the visible part of the spectrum. So, only the last 75 about 75 years or so have we been looking at astronomical objects in other forms of electromagnetic radiation other than visible light, right? So that's all that Herschel certainly had a nice telescope. It certainly wouldn't be. It wouldn't have been as good as the the telescopes we have now, of course. Uh, one of the things that we first encounter when we start studying the Milky Way is our use of these variable stars. All right, so let's talk about some of the variables that we've encountered up to now. So a variable star in general is just a star that changes brightness. So we've encountered this with nova. Remember, nova is usually a white dwarf. You're talking about a white dwarf in a binary system where remember the Roche lobes overlap, and so matter will fall onto there'll be like an accretion disk around the white dwarf, and then eventually enough matter falls onto the surface of the white dwarf, and it lights up. It explodes, and that's called a nova. And then, of course, a supernova, and we've learned that there's two different types of supernova. Type 1 supernova, which is somewhat similar to I mean, it's much more intense, of course, than a nova. So the type 1 supernova is, again, this is a more massive white dwarf, and it's accumulating enough matter to just basically blow itself to bits when it explodes. We don't think that at type 1 supernova that there's not a lot of remaining matter after the supernova explosion. But the type 2 supernova, now we're talking about stars that start their existence as, many times the mass of the sun. So usually we start thinking about maybe 8 to maybe even 25, 8 to 25, or even more in some cases, just a few cases, maybe 30 times the mass of the sun or so. Anyhow, that would be a type 2 supernova, and those things, of course, there is stuff that remains afterwards, and that they can become a neutron star or a black hole. We've learned all of that. But remember, these vary, and in some cases they can vary, not in a predictable way, like the nova can get brighter when matter accumulates on the surface, and that can happen, over and over again, but not in a predictable way. And so these are what we would call cataclysmic variables. All right, so and then there's other variables where the luminosity varies in a more predictable, regular way that you can kind of almost set a clock by it. And these things, they don't necessarily have anything to do with being in a binary system, so we call them intrinsic variables. That is, by themselves, they're variable stars. They're varying their luminosity, as in a nice, predictable way. So, two types that are very important to astronomy. These are the RR Lyra and the Cepheid variables. So the RR Lyra tend to be smaller than the Cepheids. These are just smaller stars in general, and these have periods usually less than about a day, and so they can just be like a certain number of hours. And then the Cepheids generally are variable stars that vary their brightness in the course of several days, or even up to as much as up to like maybe 30 days. There are some exceptions that go as far as like 100 days, but usually it's in the maybe a few days is a typical Cepheid. Sometimes, like I said, sometimes up to 30, 50 days. There are different ones, basically. All right, so let's, so they're showing us the picture.